this video is about properties of logarithms, and so before we get to properties of logarithms, I want to go back and remind you about rules that you learned in Algebra 1 that are properties of exponents, just so that you can see that these properties that I'm about to show you for logarithms are really not new. They're just writing the exponential ones that you already learned, but just using logs. Because remember, there's this connection between exponents and logs. They are kind of directly inverses of each other, so there's a relationship between their properties. Okay, so here are your three rules that we're going to look at today anyway. And the first one says, if you multiply together exponential functions that have the same base, in this case a, you can add together their exponents and apply that to the same base. So here's a simple example. If I had something like x squared times x to the 9th, I'm allowed to keep those two exponents on the same x, right, by adding together their exponents and making that x to the 11th, right? So again, something that you've probably used before, okay? A second one says if you're raising some base to an exponent, and then you want to raise that same base to another exponent, like we're really trying to apply m and n to this same base of a, then I can combine those by multiplying together the exponents. So here's your example. X to the 4th being raised to the 6th. I'm trying to apply the 6 to something that's already got a base or an exponent of 4, so I'm going to multiply this together. This is going to become x to the 24th. Okay. Your last example, directly related to your first one. If I'm trying to divide bases that are the same, I can subtract their exponents. So for example, something like x to the 9th over x to the 4th, I can say that's the same as 9 minus 4 is 5. This is x to the 5th power. Okay. So we're really going to look at these three properties again, but how they work with when we're talking about logs instead of exponentials. Okay, so here's the very first one, applying to that very first property of exponentials about adding the exponents. Okay, and what this one says is if you take the log of whatever base, it doesn't matter what base you use, and it's of a product. In this case, they're saying m times n. Okay, that you're allowed to split that m and n up into two logs and add together the two logs. So again, if you come back here and you see this connection, here I was multiplying the bases and I added together the exponents. When I come here, remember the output of a log is really an exponent. So really I'm just adding together the two exponents for m and n, right? So it's really the same property. So let me just kind of show you this working, right? Here's the exponential form. We know that 2 to the 2nd times 2 to the 3rd is equal to 2 to the 5th because of that property that we just saw, right? These both have a base of 2. So I added together their exponents, and I got a new exponent of 5 in the simplified version. So if I were to go to log base 2 of 32, and kind of just like, let's look at that separately, right? You can kind of say, okay, this is saying 2 to what power gives me 32? Well, the answer to that is 2 to the 5th power gives me 32, right? And we know that. So how can we look at this log base 2 of 32 maybe a slightly different way? We could also say that, well, 32 is made up of 8 and 4, right? 8 times 4 gives me 32. This property up here says that I'm allowed to give this log base 2 separately to both of the things that I'm multiplying together. In this case, I called them m and n. In this place, I'm calling them 8 and 4. So I said log base 2 of 8 and log base 2 of 4, right? Just instead of multiplying together, I'm adding together the log versions, right? And so I'm going to say in this case, well, log base 2 of 8 says 2 to what power gives me 8? The answer is 3. Okay, and this one's saying 2 to what power gives me 4? The answer is 2. And if you notice, the answer here is also 5, which I'm really just kind of looking at this up here. I'm doing the same thing down here, right? So it's really just the log version of exactly what we're talking about, except we're using the exponents only because the logs kind of are kind of asking us what the exponent is. Okay, so let's look at a couple of simple examples. Okay, excuse me. So just really quick before we talk about them. You can also take this and go the other way with it. If I give you two expressions that have the same base, in this case they called it b, and we're allowed to put together the logs by multiplying together their values. So if I have an addition sign in between two logs that have the same base, I can multiply them together to combine. So I could take this back in the other direction and say, right, for example down here, I could say 8 times 4 gives me back the 32 that I started with, right? So we might see some of those come up here. In fact, that's what we're going to see. So in this case, we're going to do that what I was just talking about. I have two expressions that have a log in them, log base 3 of 10 and log base 3 of 2, right? And so I'm saying, oh, well, I could put those together by, because there's an addition sign in between them, I can multiply together the 10 and the 2 and get a 20, right? So I can take log base 3 of 10 plus log base 3 of 2 and turn that into one expression, right? Single logarithm, when they ask that, that's one log expression, and I call it log base 3 of 20, okay? It asks us to simplify if possible. Log base 3 of 20 doesn't simplify nicely, so we're going to leave that one alone, okay? Second problem, just has log. There's no base, but since both of them don't have a base, we can assume that they are 10, right? Log base 10. And so I can combine these ones, again, just by multiplying. 3 times 2 gives me 6. X times, well, I don't have anything over there, so I'm just going to bring that along. Y times y gives me y squared. So I can turn this one to log of 6y squared. That is the single logarithm version. Again, the addition sign in between these indicates that I can multiply together the 3xy and the 2y. Okay? So here's your last example. Okay? Log base 2 of 0.5 plus log base 2 of 2. Again, I can multiply these together and say this is really 0.5 times 2. This is the log base 2 of 1. And I can simplify this one because this says 2 to what power gives me 1, and the answer here is 0. Okay? And so let's look at this a different way. Okay, you saw that worked out. I multiplied together 0.5 times 2. I had an expression that I could simplify, and I did. Okay? But I could have, if I wanted to, simplified these early. This says 0.5 is really the same as, I'm just going to write it right below it, the log base 2 of 1/2. Okay? The log base 2 of 1/2 is really -1. And the log base 2 of 2, this is saying 2 to what power gives me 2? Well, 2 to the first power gives me 2. And if you notice, this is as an exponent of -1, this has an exponent of +1, and this is also 0, right? So I can use this combining property to get a 0, but I could also, in this particular case, simplify each of the expressions, and I'll get to the exact same place, right? So different ways of getting to the same place. All right, so here's your second property, and again, relating to that division property from exponents. If we are dividing two things inside of a log, I can expand that expression, give the m and the n their own logs, by putting a subtraction sign in there. And again, the reason why is because when the bases are the same, subtract the exponents. And this represents an exponent, so does this, right? And then again, I can take this back the other way. If I have two log expressions with a subtraction sign in between them, I can take this backwards and take the m divided by the n, and I can simplify it, okay? So we're going to do that one, where I give you this expression here, right, which is kind of like an expanded expression. It's kind of all in a bunch of pieces, and I want to put all those pieces into one log, right? They all have the same base of b, so I can, okay? So I'm just going to go left to right, and I'm going to look at this. This says log base b of u plus log base b of v, right? So I have an addition sign in between these logs, which means I can combine them into one log base b of u times v, again, because of the addition symbol, okay? So I'll just call that uv, okay? And then this says minus log base b of uw. Let's fix that. Okay. Log base b of uv minus log base b of uw. Okay. And now I have a subtraction sign in between these logs, and my rule up here says you're allowed to divide these values. This would become the top value. This will become the bottom value. This is the log base b of uv over uw, okay? Excuse my terrible writing today, uv and uw, okay? And so the nice thing about this is by combining this all into one big log expression, I'm actually going to be able to do a little bit more simplifying here, because if you notice, there's a u on the top and a u on the bottom in our simplified expression, so I can actually turn this into the log base b cancel of just v over w, right? So this big long expression, log base b of u plus log base b of v plus minus log base b of uv, is really the same thing as just this much simpler expression, okay? So let's apply these two rules, right? How could this be useful to us, okay? If I tell you, for example, in this problem, I'm giving you this information that log base 2 of 3 is 1.59, okay? Like, that's not something that we would know without a calculator and without some help, okay? So they're going to tell us that, and they're going to ask us, well, what's the log base 2 of 12? And really what this problem is saying is 2 to some power gives me 12. And we're kind of like, well, 2 to the third is 8, 2 to the fourth is 16, so like maybe somewhere between 3 and 4, but we don't really know exactly where, okay? But here's what I can do. I can take this expression and I can expand it, okay? I'm going to turn this into the log base 2 of 3, and I did that because I know that that's about 1.59. And so the other expression, if I expand, remember the rule says that I can take a multiplication problem and expand it. I'm really going to turn 12, right? This 12 I'm going to turn into the log base 2 of 3 times 4. Right? 3 times 4 gives me 12. Right? And I did that because I know the log base 2 of 3, right? And I also know the log base 2 of 4. Okay? So that if you notice, if I were to put these back together, I would get log base 2 of 12. And the reason I did this is because the log base 2 of 3 is, they told us 1.59. Okay, and the log base 2 of 4 is this 2 to what power gives me 4? Well, the answer is 2. Okay, and we can say that, okay, well, this looks like it's about 3.59. Okay, so we can get an estimate. If I know kind of some of those strange values that I don't know, I can maybe break it up and figure it out from there. Okay, so here's another simple example of that. If I say the log base 2 of 3 halves is the same as the log base 2 of 3 minus the log base 2 of 2. Again, there you go. I have the log base 2 of 3 is 1.59. Okay, and the log base 2 of 2, this says 2 to what power gives me 2? Well, the answer is 1. Right, and so I can say the log base 2 of 3 halves is about 0.59. Right, so this has some pretty good applications for us. We might be able to break up a complex expression like log base 2 of 3 halves into some simpler parts that will combine very nicely for us. Okay, so let us go on to the last property. Here it is. Okay, so the last property is kind of going along with that second one, which was saying if you have two exponents that are trying to get to the same base, we can multiply them together. This is going to be directly related to this one right here. So this is an exponent, right? Okay, and then this big log thing represents an exponent. So what we're claiming is if I want to take this n and I just want to multiply it by log base b, I'm kind of taking this expression and I'm kind of like saying, let's bring it way out here, because the exponent rule says I can multiply the exponents together. Well, n is an exponent, obviously, but remember that this whole big expression represents an exponent as well. So I'm allowed to multiply together the exponents. So I can just put these two together. So here's a good application of this. If I say log base 5 of 25 to the 4th power, if you go to your calculator and you type in 25 to the 4th power, you're going to get a pretty big number. I'm actually going to find out what it is right now. Okay, 25 to the 4th power is 390,625. Pretty big. Don't want to have to figure out the log base 5 of that. So instead what I'm going to do is I'm going to rewrite this. I'm going to take this 4, which is an exponent inside the log, okay, and I'm going to bring it outside and just multiply it by the log. 4 times the log base 5 of 25. And this is way easier because this is saying log base 5 of 25 is saying 5 to what power gives me 25? Well, the answer is just 2. So the final answer for this whole problem is 8. That is way easier than figuring out that 5 to the 8th power is 390,625, right? So just something to watch out for. Okay, so we're going to move on. Okay, we're just going to simplify, again, some of these expanded expressions. How can I take these big expanded expressions and write them in a more simpler log form? Okay, so here's the way we're going to do this. We want to get all of this information, the 4, the 2, the 3, the y, all of those values inside of one log, if that's possible. And in this case, it is possible. Okay, so what we're going to do first is we're going to get anything that's floating around outside, this 4 and this 3, and we're going to bring them back inside the log. Okay, so it's actually the opposite of what we just did. Remember, in our problem before, we had this log base 5 of 25 to the 4th, right? We actually took the exponent from the outside, or from the inside, and we moved it to the outside. Well, I can do that in reverse as well. So we're going to take this 4, okay, and we're going to bring it in here, and we're going to attach it as an exponent to whatever's in the log, which in this case is just the 2. And I can do the same thing with this 3. I'm going to take this 3, okay, and I'm going to bring it inside right here. Okay, so let's do that. It's going to say the log base x of 2 to the 4th minus the log base x of y to the 3rd. So that fixed our first problem in that we got those coefficients inside of the log. Well, 2 to the 4th power is 2 times 2 times 2 times 2, which is just 16. So this is log base x of 16 minus log base x of y to the 3rd. And remember, we also just had a rule that says as long as the logs have the same base with subtraction, well, that means that we can divide the inside pieces. So I'm going to turn this into one log. The log base x of 16 over y to the 3rd power. And if you notice, I was able to take all of those values, the 2, the 4, the 3, and the y, and I was able to kind of crunch them up into one simplified log expression. So that's what's called condensing our logs into our log expressions into one log.